time is now 12 p.m. Central Time, and I'm your host, Dr. Matthew Richardson, and today I will be talking more about the research that I'm currently working on. But before getting into all of that, I'm going to go ahead and do what I typically do, which is verify that I'm actually streaming. This is always the period of my stream that scares me the most because it's always the question of whether or not Twitch is going to act right and allow me to, one, verify that I'm actually streaming, and two, see everyone's chat. So fingers are currently crossed right now. Okay. If you guys can see me, that's great. At the current moment, I cannot see you or hear you. Um, I am logged onto Twitch, and it's still showing that I'm offline, which is troubling. My OBS software is showing that I'm live now for about a minute and 30 seconds. Either Twitch has not caught up yet, or I'm not streaming. Let's just hope it's the former, not the latter. Okay. I'm seeing the little red dot that indicates that CosmoQuest X is live. With 0 viewers, but that's cool. And there actually might be viewers here. It's just that, like I said, Twitch is always giving me issues at the very beginning. All right. But yeah, if you guys can see me and hear me, got some good news. So I did some tests for my algorithm, my incidence angle algorithm, which I'll re-explain in a minute, as I've explained in past streams. And I got some good results. But along with those good results, I got some possibly troubling results as well, which I'll get into in just a moment, once I'm actually able to verify whether or not I'm streaming. All right. I'm going to open up Slack because typically when I run into problems, the Weekly Space Hangout crew, who like faithfully watches my streams, thank you guys, always help me out. All right, so went live 3 minutes ago. Let's go ahead and watch. Let's see if this changes anything. All right, there I am. And 9 people. I gotta say hi to everyone. All right, I'm gonna go ahead and close Slack because that's just gonna slow my computer down even more. Let's go ahead and pop out chat. Okay. Thank you, Uncle Bill Druin. So, yeah, there might be a little bit of lag. Hopefully it's not too bad. All right, so let me go ahead and just jump into what I wanted to talk about today. So you guys have been present for my previous streams, me talking about, thank you, Keeper of Maps. Also, I think based off of my previous streams, you're probably at work right now, so I don't want to mess anything up there. And again, thank you even for watching from work. Thanks. But hey Peter, hey Guido. That's right. Let me go ahead and say hi to everyone. I'm just gonna probably repeat some names. I'm gonna go down the list. Hey Guido. Hey Keeper of Maps. Hey Larry of the G Cloud. Hey Michael T Mayer. Hey Oscar 65. That's a new name. Welcome to today's stream. Hey Peter. Hey Phoenix. Hey, is that? Let me make sure I get that right. Side Sidemt, I believe, or Sidert, if that's an R. But hey, welcome to today's stream. Hey, the Lou. Hey, Uncle Bill Drew, and hey, Zarin. Guys, welcome to today's stream. And today I'm talking about the progress I've made on my incidence angle analysis code, where the purpose of this code is to determine how incidence angle on the lunar surface. And to give a little background to that, we have some images that were taken by the Lunar Reconnaissance Orbiter of the Moon. And we're using these images for a citizen science project called Moon Mappers through CosmoQuest. If you guys get the chance, check us out online. We're located at cosmoquest.org. Um, but yeah, we have these images taken of the moon, and we want to know, how does the incidence angle of the sun, that is, how does the angle at which light from the sun hitting the lunar surface affect how our citizen scientists are marking the craters on the lunar surface within these images that we have? And so I'm doing this analysis. I have access to all the data that I need access to at the very least. Um, and I'm updating you guys on the progress as well as showing you guys some of the stuff that I've been doing recently. So let me go back to chat. Oh, perfect. Um, that's right. This is around dinner time for some of you guys. This is lunchtime for me. So after the stream, I will definitely be eating. I got the name right. I'm happy to hear that. But right. So right. Let me go ahead and show you guys what I was able to find out through my incidence angle analysis that well seems correct. And the first time I saw it, I was thrilled. And basically, the information I'm about to show you is the fact that my incidence angle analysis is able to pair images that match each other. That is, if I have one image and another image, and I overlap them, some region within both images overlap one another. It's perfect overlap. And so I was happy about that. And so let me go ahead and bring that up. What you guys are currently seeing on my screen is the typical windows that I use to conduct my work for this analysis. But I'm going to go ahead and I'm going to add a new scene. So let's copy and paste this scene and make the modifications I need to make. So let's duplicate. I'm going to call this scene 3. And let's pull up some images. But first off, let's find the images that I need. So, what modifications have I made to this before I end up doing that? It's the make file. So right now I'm looking at the main program for my analysis called Incidence Angle Analysis. And right now I'm trying to pull up that result that I was able to obtain that showed that my algorithm appears to be working correctly. Let's just go with this one. And so throughout my code, I typically put little areas where I can check things, print stuff to the screen. And so that was just me uncommenting one of those checkpoints. I'm going to try my best to keep up with actually talking while I'm doing this stuff, because I've noticed in my past streams that I'll kind of like just get into like programming mode, and typically when I'm in programming mode, I'm extra quiet. And that's so good for a stream, right? Gotta be talkative. All right. And so at the current moment, if you guys are making comments towards me, I can't see them, but I will look at them in just a second. All right, so program compiled. Hopefully it's going to show me exactly what I want to see. If it doesn't, let's hope that's not an issue. I don't think it should be, though. Let's go ahead and clear the screen first. Let's run the analysis program. I'm gonna do that so it doesn't run through all the data that I should run through. But let's see what happens. And note that the amount of time it takes to actually run the algorithm is going to probably take longer because of the fact that I have a lot of other um, apps open right now. Mhm. All right, let's pray and hope that it's going to give me exactly what I'm looking for. It should. So right now, there we go. All right. So what I've had put out to the screen here are the various times it's taking to run through certain things in the algorithm. As you can notice here, there's 25 seconds worth of time. There we go. Hopefully that's highlighted within the actual stream I'm showing. But the 25 seconds worth of time is from me pulling in information from one of the tables. It typically takes about 5 seconds, but of course, because I have all these applications running on my MacBook, it's going to take a little bit longer. So everything is probably like a factor of 5 times longer in running. But at the very bottom here is the key information I want to get to. This is showing all of the paired regions between two different sub-images that have been paired with one another because of the fact that they have regions within the images that overlap one another. And the things I should note about these sub-images is that each sub-image comes from a master image. And so to kind of give you an example of what one of our master images looks like, I'm going to switch scenes. And again, I'm going to get to the major thing I discovered with this. But let's switch scenes. You're going to see an image that I don't want you to want. I don't really care about, but it's not the image I really want to show. So this is actually one of our master images that we have from for our Moon Mapper app. But the problem is that, well, not the problem, but the situation with this particular image is that it's actually a slice of the true master image that's stored on the Lunar Reconnaissance Orbiter image archive. So let me actually get you one of the more like complete images that we have from that archive. Let's open up I'm using GIMP. I love GIMP to view the images right now. So let's change this one. Let's open. Perfect. And so the actual images that we're viewing are thumbnails. So it's the same image, it has a reduced resolution, and because of that, it's a much smaller file. So let's see. Let's find another image. That's nice. Okay, I think this one should work. And hopefully you guys will see what I see. You should be able to, though. Okay. It's taking a lot longer than I expected for it to load that image up. All right, we're going to do this a different way then. I'll use this one. Open with GIMP. Let's see if you guys can see that image. So I'm going to open up my OBS software and see. And no, you cannot see it, but that's cool. I'm going to fix that problem. So scene one, let's go ahead and add another window. Second image. It should have it there. Interesting. Let's go with that one. All right, perfect. I'm going to remove this image. I'm going to slightly modify this so that you can see the entire image. Window capture. Yep, let's remove that. And this, ooh. Okay, stretching an image where it doesn't have proper aspect ratio is, it gets weird. All right, let's just do that. So you're gonna kind of see like void, my face, at the very bottom right, and then one of the more fuller images that we have. And so I must note that this particular image that I'm showing right now is it's at reduced resolution, so I can't really like zoom in because if I do, it'll look all pixelated. But this is actually one of the, or it's an image of one of the master images that is stored within the Lunar Reconnaissance Orbiter's image archive. And so this is the image of one of the fields that has been imaged by by the NAC camera system on the Lunar Reconnaissance Orbiter. And this is what you'd kind of get for a typical image. I think you can see the entire image within this. Yes. Um, and so what we typically do with these images is we'll take a master image as you see here, and we'll slice it up into much smaller images at higher resolution, well, at various resolutions actually. But we'll slice the image up, and those are the images that are actually being annotated by our users. So let me go ahead and take a moment to kind of like look at comments because I know it's been a while. Oh, hey Phoenix, I'm happy you're back. No problem stepping away. Understand. Um, yeah, I think it's hopefully it's gotten better now, Uncle Bill. But yeah, I hope it stays good for the rest of the stream. So yeah, that big black void on the right hand side of the screen. Or wait, is that the dark or our side? Oh, you're talking about the actual image. So from my understanding, these are actually images of our side of the moon. And so okay, never mind. You're making a joke, Guido. No problem. But for anyone who doesn't know, so the moon is tidally locked to the Earth. That is, well, what that means is that the moon's intrinsic orbital rotation is equal to its 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 orbital that came out wrong. The moon's intrinsic rotation is equal to its orbital rotation. And because of that, we only really see one side or one hemisphere of the moon. Always see that one hemisphere of the moon. Well, it's that's not exactly true because of the fact that the moon itself, it would be true if the moon's orbit was perfectly circular, but because the moon's orbit is a little eccentric, it has a little bit of eccentricity, blah blah blah. Wow, my words are coming out bad right now. Because the moon's orbit is not perfectly circular, it's a little off circular, for lack of better words. Um, we actually see roughly 50 to somewhere, I believe, to 60% of the moon throughout the year. Um, thank you. Uncle Bill said it perfectly. The more technical term for it is like libration or liberation. It's just a Pink Floyd album. Oh man. Oh, you guys have a great sense of humor. Um. Okay, so what's the so Zarin asks, what's the typical average resolution of the images that users annotate? And so the resolution of the master images is somewhere around, if I'm not mistaken, zero point 0.5 meters per pixel. We modify the images to, I think one calculation I saw was one of the images was modified to be about like 1 meter per pixel. But yeah, we have different zoom levels that we use for the images. Yes, not to be confused with drinking certain substances. um, Oh, thank you, Zarin. Okay, thank you for that correction. I apologize if I get you guys' names wrong. I'm so sorry. I don't mean to do it. It's an accident. But of course, call me on it. Be like, that's not my name. No tomato here. If it's tomato, call me by tomato. All right. So this is one of the master images that we have, and we cut it up for our users so that they can be able to better mark craters versus trying to mark craters within an image this big. And of course, an image this big is going to be very hard to see much smaller craters, which is another reason why it's great to just cut them up to smaller slices. All right. So let's actually get back to what I was able to find. So I'm going to go ahead and switch scenes again. Let's find the right scene. Perfect. This scene works. And one of the very first results that I'm getting here, which is going to be line 0, is that I've matched two images to one another, specifically, or two sub-images to one another. I've matched this image M115 blah 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 _1 _529, where the first bit of that entry, the M all the way to the E, corresponds to the master image's ID. The next character in that sequence past the first underscore, the number 1, corresponds to the scaling level that we're currently using. And so as you move from different numbers, 0, 1, 2, 3, as you'll see, each number corresponds to a factor of 3 in zoom level. So going from, let's say, for example, from 1 to 0, an image that has been tagged with a 0 is zoomed in 3 times as much as an image tagged with the number 1. And then the very last number of this image ID is the number that is the image is the numbered image of that particular set. So this, for example, for the example I'm showing here, this is the 529th image that of the master image M115008450R at its zoom level 1. All right, so what I'm going to go ahead and do is I'm going to find this image online. And so to find that image, I can just simply copy this particular image ID. I'm going to go over to the MySQL table database that stores all of our information. I have my own personal copy on my laptop. And I'm going to go ahead and find this image. So select. Whoa, what happened there? Okay, weirdness. All right, select from, this is images where name equals that. It should give me one entry. There's the one entry. And so with this, what I've done here is given myself the ability to be able to find or gain access to the link for this particular image. I mean, as long as you have the link, you can actually see these images online. So you're not going to exactly see what I'm doing here. I'm going to go ahead and go online and actually get this image. I'm going to download it to my laptop, which should be very fast. And then I'm going to bring up the image for you guys to see. Let's open this image. Let's save this image as image1.png to my desktop. All right. Minimize. And I'm just going to pick a scene. Let's use this scene. This scene works. So again, my screen's going to have a lot of black space, but it's okay. I'm going to bring stuff back to get rid of the black space. All right. Desktop. There should be image 1. Give me 1 second. I'm bringing it up right now. And again, the reason why I was able to get this far was of course because of help from my fellow CosmoQuest team members, and then you guys, being right there with me over these past few weeks while I try to explain things, and then you guys are correcting me like, okay, think of it like this. So again, like I said before, thank you guys. All right, so here we got that. That's the first image. And I'm gonna try my best to like keep the aspect ratio right so that you guys can see these things the way they should be seen. And so I'm now gonna pull up the image that it's been paired with. So let's go to that image. Let's use Safari for this. It's fastest that way. Wait a second. Did something wrong. Let's fix that. Got to go back to my MySQL database, get the link. This is definitely one of those moments where I'm like, fingers type fast, fingers type fast. All right, so save image as image2 on the desktop, .png. Save it. Open it. My computer's really upset with me right now because I'm making it work hard. But that's cool. It'll be okay. So let's go ahead and open up this image as well. So image2. And should be there as well. So I'm going to now move this image. And I'm going to try my best to kind of have these images side by side. What's the best way to do this? All right, I'm going to bring my face back for this particular. All right, so these two images have been paired with one another. Right? These two images correspond to, and if I go back to here, these two images are basically this first line of information. These are the images that have been paired with one another. And when I first saw this, of course, my idea was to visually verify that these are actually indeed images that, overlap. The one thing I want to note about these images is that they come from the same master image. However, they are at different scales of that master image. So one image is more zoomed in than the other. So what you'd expect then is that the one image is more zoomed in should probably be within the its entire region, that is, should be within the other image that's more zoomed out. And that is the case. And I'll show you right now. So I'm going to do some zooming on these images so you can better see the reason why the left-hand image is physically within the right-hand image. Oh, Peter, so this is so all the images that I currently have should be from the side of the moon that's facing Earth. So I apologize if I didn't answer that question earlier. So let's get to these images. Let's pull them up. I think I can see them both preview. All right. And I'm going to zoom in to the on the right image. I'm going to do a little bit of zooming. And if you notice, now that I've zoomed in, they look pretty similar, don't they? Oh, my face is in the way. Let's move my face. There we go. you can now kind of see, now that I've zoomed into the right image, that the features are pretty much the same. Yes, so these are images from the near side. And so basically what this is saying is that, hey, my algorithm is able to match images, or match the sub images to one another. At least images that come from the same master image, but at different scales. And so I was pretty happy about this until I started looking a little bit more closely at the physical values that I was getting. So I'm going to go ahead and switch scenes again back to this. And so, of course, to be able to do this, I have to establish a coordinate system, so that the computer knows exactly where these images are at and how they should be overlapping. So the thing that kind of troubled me is that my understanding of how the images are able to know, or how the algorithm is able to identify how the images should be able to overlap, is that I establish a coordinate system. In this case, it's a Cartesian coordinate system, so it has an x-axis, y-axis, and then from there, for the master images, I'm given the, and so I'll switch my tab on my terminal window, and so for each master image, so select star from image sets. And I just limit it to one. That's all I really need. So for each master image, I'm given the maximum and minimum latitude and the maximum and minimum longitude, basically creating a bounding box. And I got this word from Keeper of Maps. Perfect way to put it. But basically, creating a bounding box for each image, so that my algorithm can know exactly how the images are oriented. There's a little bit more to that because I had to actually go get some external information to figure out which edges of the images correspond to either the minimum or maximum latitude or longitude. But once I had that information, I was able to clearly tell the algorithm, hey, this particular edge of the image is either the maximum or minimum latitude, and I was able to move from there. And moving from there, I've been able to get to where I'm currently at. But the problem is that even though the images are being matched, based off of the numbers I'm seeing, they don't appear to be being matched the correct way. At least not the way that I have in my mind on how they should be matched. And so, to continue to explain what I was going over, is that I established a coordinate system. I tell the algorithm, given that coordinate system, what the upper left hand corner is. That is, what is the latitude and longitude of the upper left hand corner. Now, when we see an image, of course, and we see the upper left hand corner, we just see the image however it's oriented. But as far as the computer algorithm is concerned, the way in which the image is oriented depends on the physical values of each corner. So it might actually remap how the or reorient how the image is actually oriented as it sees it. So that's cool, but the thing that really kind of confused me is that the upper left hand corner of each master image is able to know where the origin is at. And for each sliced image that comes from a given master image, that sliced image should know where the upper left hand corner of the master image is at. And this bit of information is very important to be able to determine where features are at within each sliced image. However, when I went to look at the physical values that I was getting for these particular sliced images, which are given here, and I'm going to go over exactly what these values are. I just noticed that the values weren't exactly what I expected them to be. So let me go back to make sure that I'm not missing out on any comments here. Okay. All right. So what I'm going to do now is I'm going to go ahead and pull up pull up the larger image in GIMP. And so the larger image based off of this information is the one, of course, that's scaled out at a scale level of 2. So that's my second image. So let's go back to a different scene. Or better yet, let's go to scene 1. And with scene 1, I'm going to go ahead and reopen GIMP. And we'll open up this file. So let's go to the desktop. And I believe this should be image 2. So we're going to have to do some math, of course, for this to actually work out properly. So I've done the math. It's just that I noticed that whenever I get on these streams, I'll do math and like my brain will just completely like shut down on me. Um, so we're going to window capture, and I'm going to put this as image 2 for this one. Okay. Oh, can't use that. Image 3. So where is it? I think it's this one. It's not that one. Wait, did I open the image yet? Give me 1 second, guys. It might be a little bit easier if I actually just remove some of this stuff. Let's see. It's definitely this one. And it should be entitled image 2. All right. Window capture. Just name it as that. And there we go. All right. So let's go ahead and let's expand this image. Well, if I expand it, then it's gonna probably start to look weird. You know what? Yeah, let's go ahead and expand it because really, what all I care about are the X and Y axis that you see along the upper and left edge of this window. So I'm not really even worried about what the features look like within the image. I'm really just more so worried about the physical values along the X and Y axes. All right. So note, the image that we're actually seeing here is an image that I've grabbed from offline or online, excuse me, and this particular image has I think a pixel. I think it's a 450 by 450 square pixels. Whereas in our database, I don't believe that that's the actual dimensions of the image. So let me go ahead and check that, so you guys can see what I'm seeing. I'm gonna go back to this one. Hi, Adam. Welcome. All right. So let's go ahead and select from images where this should be name is equal to that. And so as you guys can see here, though, the actual image dimensions are 450 by 450 because the image has a width of 450 pixels or 4050 pixels and a height of 4050 pixels. So I'll just quickly highlight that. So the image has been scaled down such that the X and Y axes have been reduced by a factor of 10. So I need to keep that in mind. All right. So let's now go back to the actual results I end up getting. Now remember that the upper left hand corner of each image, whether it be a master image or a sliced image, is the most important corner for that particular image. In the case of the sliced images, the upper left hand corner is how is origin for any sort of features that are within that image. And as far as the master images are concerned, the upper left hand corner is the origin for any of the sliced images. And then going one step further, outside of that, the origin itself, the origin I've defined for the computer algorithm, simply needs to know where the upper left hand corners are of each master image. And using this information, I can establish a set of vectors that will allow me to identify features within each sliced image. All right. So with that said, and hopefully that made sense, and if it didn't, I can sit here and probably try to draw something out so that it'll make a little bit more sense. But basically, in order to determine features within any sliced image, I need to be able to establish a set of vectors that go back to the origin. All right. I am so sorry to hear that, Guido. Um, yeah, if you guys have any advice as to how I can make modifications to the stream so that it runs a little bit more smoothly, guys, by all means, let me know. I believe about a week ago, Guido informed me that I could get the stream to run a little bit better by reducing the output resolution, and I did that to 720p, and hopefully that's made a difference. But I think at the time he was on his tablet watching. All right, so what was I trying to show? Right, I was trying to show that the way in which the computer algorithm is identifying the origin is not what I expected. So getting back to what I'm showing here in the bottom window, this information corresponds to all the information that I possibly need to be able to do my analysis on this particular pair of images that have been matched to one another. And so if we look at the the fourth and fifth column, which would be these values here. Lower the frame rate. Okay. Yeah, what I'm going to probably do is read up a little bit more on exactly how I can make modifications to my OBS settings so that things run a little bit more smoothly on your side. So as I understand it, my output is set for 720p. So Nippy. Oh, okay. So Nippy, I guess I wouldn't mind playing things if you guys would like that. Um, Playing something in the background. If you want me to play something, by all means, I'll do it. Just make sure you send it to me in advance, or like you've done now. You've sent this to me, and I'll review the song to make sure it's appropriate. And then if it's cool, I'll play it. Hey, Susie. But yeah, thanks, Nippy. I'll definitely check this out. Let me go ahead and save it somewhere so I don't forget. Yeah, the last thing I want to do is start playing some music, and the music isn't what I expect. Then the stream goes someplace that I don't want it to go. All right, that's all right. So your tea glass brought down the Wi-Fi. Wi-Fi. All right. So right. So I wanted to be able to show that this particular coordinate is not what I expected it to be. And the way in which I was able to determine that is that already I know that these two particular values correspond to the x and the y coordinate respectively for the upper left hand corner of the image that I'm showing here. So I'm going to go back to those values. Yeah, these two values that I've highlighted are for the upper left hand corner of that image. Or at least they should be. But then what I immediately noticed though is that for the overlapping region, and I'm going to go ahead and pull up those coordinates. The overlapping regions, its upper left hand corner for a not for a lack of better words, but its upper left hand corner shares the exact same um, coordinates. And so when I kept looking at them, I kept thinking to myself, like, wait, this isn't making sense. How is it that the upper left hand corner of my master image, or not my master image, but of my bigger sliced image, shares the exact same upper left hand corner of the overlapping region, where I know the overlapping region was the second image, was the entire region of the second image, and I know exactly where they match was which was the lower left hand corner of this image. And so to kind of like make sense of all what I'm saying, I'm just going to draw a box around where they overlap. So I'm going to go ahead and use my tools here. Open up the toolbox for GIMP and see if I can select a region. And hopefully you guys can see exactly the region I'm selecting. I think this is it. And so it should be roughly in this area here. Kind of sort of in this area. I'm kind of ballparking this, but that's the overlapping region. And I noticed that the coordinates they're sharing the upper left, well, what should be the upper left hand corner of the image I'm showing here shares a coordinate or shares a corner with the overlapping region. And so that immediately let me know that something was wrong, at least with how the computer is identifying the coordinates within an image. And so now I'm kind of at the point where I'm trying to determine exactly how is the how is the computer identifying coordinates, and what should I do to modify it so that it identifies coordinates the way I'm imagining in my mind. But I would get into all of that, but I'm now realizing that there's only 10 minutes left, and I'm not even going to be able to be nearly finished with it within 10 minutes. But you know what? I might as well go ahead and just give it a try. Let's see if I can make quick progress with it. All right. So to do this, I'm going to have to go back into my code. So I'm going to go ahead and switch scenes. And I'm going to start printing out some values to see what's making sense. So of course, to do this, I start off with my main function. So let's go ahead and pull up that window so that I can see it. And the very first thing I'm going to want to do, of course, want to do, excuse me, is verify that the computer is calculating the upper left hand corner of the master images correctly. And so I can go to this function here. It's a part of the utilities class. And I already have the source code for the utilities class opened up here. And so I can go to that function. And what was the name of that function again? Calculate master global XY. So let's go ahead and find it. That's calculate subglobal XY. And this is calculate master global XY. And so within this for loop, and this for loop is actually looping over all of the master images that we have in our database. And so if I switch tabs, this file that I have open here shows that we have, which should be 26. I know it reads 27 as the last entry, but the very first entry is just basically the header. So we have 26 master images within our database. And so what this function will end up doing, along with the information that I'm showing in the far two right columns of the window at the bottom, what the function does is it calculates the x and y coordinate of the upper left hand corner of an image. And to do this, it's going to end up converting the latitude and longitude coordinate of that corner into more physical units. And so with my algorithm, I'm doing the conversion such that I'm mapping the latitude and longitude coordinate system of the moon to Cartesian coordinates where the units are in units of meters. And I'm basically doing this using the, what formula is that? It is the arc length formula, where we know that the physical distance away from some origin, let's say represented by some variable s or arc length, is equal to the radius of the spherical object times the angular displacement from the origin. And so this is a perfect equation to use, I feel, because we already know that the coordinate system on the moon, when given latitude and longitude, is in units of degrees. So this is a great equation to be able to use to make the conversion from those spherical coordinates, latitude and longitude, to Cartesian coordinates, where of course we're just we're taking an arc length and we're just flattening out the arc length. All right. And if you guys have any suggestions on that, or feel that that's not being done correctly, by all means, voice them, because this is what I came up with, and I think it should work out just fine, actually. Thank you, Uncle Bill Join, for telling me that. I'll currently leave it at these settings, and hopefully for future streams, everyone's computers won't have any problems. All right. So I was in the process of explaining how my algorithm establishes where the upper left hand corner is for a given image, master image. And so the very first thing I would want to do, of course, is verify that the calculations that it's making for the upper left hand corner is correct. So what I can do here is I can output that information to screen. And so image sets, this is a vector, and this vector stores all the information, all the important information from the MySQL database. Specifically, it stores information related to each image. So if I was to pull up the image sets again and use this as an example, let me make sure that you guys can see what I'm seeing. You can. Perfect. The information that's important for me to store, of course, would be the name of the master image. I don't need the application ID because the application ID is linked to each project that CosmoQuest um, currently has, or not even currently has, but has had either now or in the past. And the application ID of one corresponds to the Moon Mappers app. So I'm only looking at data or images that are associated with the Moon Mapper app. I don't need to worry about priority or the sun angle. However, the other information that's important to me are the minimum and maximum latitude and the minimum and maximum longitude. And also, there's one more bit of information that's important, which is the pixel resolution. I need that information to be able to convert things that are in pixel space to a more physical space, which in this case would be meters for me. All right, so let's go back to this. So what I want to do here is I want to make sure that I'm making the calculations for the upper left-hand corner correct, where the x coordinate would correspond to the longitude and the y coordinate should correspond to the latitude. So I can actually output this information for each image, which there's only 26 of them, so it shouldn't be much information it's outputting. So I need to quickly remind myself, though, what the function is for those values. And I can do that by, I'll use this extra terminal I have here. Source, or better yet, let's go to the include directory, because that will just give me all the functions for each class that I've created. So yeah, I've created quite a few classes here. It looks like there are 1, 2, 3, 4, 1, 2, 3, 4, 5. 5 times 4 is 20. 1, 2, 3, 20. So I've created 26. It looks like there's 26 classes here, each with their own functions. It does their own thing. But the class that's important to me now is the image sets class. So I'm going to go ahead and do just a quick less on image sets. Or better yet, no, that's wrong. I want the images class because the image sets. What am I getting wrong here? No, I want the image sets class. What am I talking about? The image sets vector is composed of image sets information. So, all right. So I want to be able to get the global x and global y values. So just do a quick copy and paste. Let's put some space between these things. Yeah, let's do this. I think that this should do exactly what I want it to do. Perfect, and all I have to do is change this to y. So what it should output are the converted latitude and longitude coordinates of the left-hand corner of each master image. So I'm going to put an exit in this so that I don't go anywhere beyond this. It's 12:59. I'm going to run out of time. I'm not going to be able to actually show any real math calculations. But it's going to compile. While it compiles, let me go ahead and check comments. So which Star Trek is that actually? The TOS one. I don't know what that abbreviation stands for. All right, so let me go ahead and run this so it's clear. Let's run it. It should give me what those values are, and then of course I would have to make sure it's calculating those values correctly. In my mind, I think it is. I don't think it's having a problem calculating it. Oh, the original series. Okay. Yeah, I need to catch up on the current Star Trek series. I can't remember exactly what it's called. I think it's yeah, someone tell me what what the current one is. It's pretty good actually. But yeah, I'm pretty well. I'm going to verify this, of course, off stream. Not Enterprise. Um, Discovery. Yes, yes, Discovery. I like Discovery. It's pretty good actually. Ah, it's the disco. Gotcha. But yeah, I like Discovery, and I've seen all the other ones as well. All right, guys, this is now one. It's 1-on-1, and I'm definitely gonna go grab some lunch. Thank you guys for sitting in with me today as I talked about what's going on currently with the research I'm doing. Um, I'm definitely gonna go ahead and finish doing what I'm doing now and do some other stuff to make sure that everything's working properly. But thanks for stopping by. I will be back on Friday at 12 o'clock Central Time, and I'm unsure if I'm going to be still talking about this. I really want to get to doing something else. Pick a topic and then we just talk about that. That's not my research. Something else is astronomy related. But again, guys, thanks, and I will see you all next week. I've learned that I should not end my stream just yet because if I do, there's a possibility that because of lag that you won't see the end of it. So I'm just going to go ahead and I'm going to look at comments. Thanks, Adam, for coming to the stream today. It's great to have you here. Thanks, Phoenix. But yeah, I've learned my lesson about that in the past. Thanks, Peter. All right, guys. Well, until next time. Bye. A quick thank you to Guido and to Uncle Ben for saying thank you to me. All right. I'm really out this time. Okay. Bye.